Hello, my name is Plerntilase.
I'm Polisa Tianyamanan, and we're from International Community School in Bangkok, Thailand.
Today, 422 million people worldwide have diabetes. Of those, 51 million of them have DFIs, diabetic foot infections, and the root cause is not getting any easier. Resistant DFI causing bacteria are increasing. Staphylococcus aureus, the most prevalent pathogen, is associated with treatment failure, expensive hospitalization, and high morbidity.
Staphylococcus aureus colonizes diabetic wounds as highly persistent biofilms, which are bacterial communities in a polymeric substance that attach to the wound. These biofilms can cause delayed wound healing and premature cell death. Therefore, our goal is to develop a drug that alleviates S. aureus and inhibits biofilm production while avoiding antibiotic resistance. So, we chose to conduct Nanobody Mediated Inhibition. There are 3 steps. 1. Biopanning and ELISA. 2. Biofilm inhibition assay. And 3. Computational docking.
So how exactly do we do this? For in vitro methodology, the first step is biopanning. We coated plates with S. aureus oversampled with phage library and removed unbound phages. Then the eluted phages are infected, amplified, and precipitated in E. coli Tg1. Next is indirect ELISA to estimate how well the phages can bind to S. aureus. We picked 30 colonies to incubate with S. aureus, antibodies, and the enzyme substrate. Finally, we terminated the oxidation reaction and recorded the absorbances. The results show that phage clones A7, C1, and C3 can bind to S. aureus. Finally is biofilm inhibition assay, where we incubated phages and controls with S. aureus in varying concentrations and time. Crystal violet was added to stain remaining biofilms. Then we recorded the absorbances. The results show that A7 and C1 phages demonstrate effective dose-dependent inhibition of S. aureus biofilms.
Next is to computationally dock S. aureus and phage nanobodies. First, we created models of extracellular S. aureus proteins. Using sequences from NCBI and UniProt, we created 22 protein models in Swiss model. 2 of them are shown on the screen. Second, we created models of the nanobodies by determining the nanobody sequence and locations of CDRs. Then, the nanobody models were created in Swiss model and PyMol. Finally, we docked the phage nanobodies with S. aureus proteins. The A7 nanobody bound best to the S. aureus protein leukotoxin D, and the C1 nanobody bound best to glutamyl endopeptidase. Their total binding energies are shown on the screen. In conclusion, our nanobodies can bind and inhibit biofilms by up to 95%, as our computational models show. In our world, bacteria with antibiotic resistance increase, and diabetes rates rise every day.
We hope that through nanobody-mediated inhibition, nanobodies like ours will be the improved alternative to conventional drugs, so patients can heal from diabetic foot infections safely and efficiently.